research center on the on our plasma related research facilities at this microelectronic and nanotechnology center. Now you can see the screen. Okay, I don't know if I have shown everyone here. So this is actually the building of our research center. This was set up in 2012 or something like that. So 2012, yeah. So it was quite old already. So now it's almost 10 years. Almost 10 years. So we have the office area here. Okay, so the color is so this is the area we have an office, and then on the right hand side here, right hand side is actually our lab. So we have everything under one roof. So we have the student area, also the staff also is in here. And then, okay, sorry. So the area here is the office, as mentioned. Okay, sorry. Actually, the spotlight. Okay, and then as mentioned, most of our staff is graduated from Japan. So you can see we have this Japanese character in the lab. So we try to adapt on the Japanese style here in our center. This is the office area. So you can see the student is inside these rooms. So we have the lecturer room here. And then this is the lab. So you can see it's a glass door window, glass door wall that we have. So everybody can see what's happening inside the lab. And we can have a nano wall over here. So where we put a picture of a nanomaterial. So we use the scanning electron microscope to observe a nanoscale material, and then we have the atomic force microscope. So we put this all nano wall that we call here. So you can see, we can demonstrate to our visitor. So we can show to them what are our capability that we can do here. So this is more image on that. So you can see we have a nanostructure, a nano ball, nano rod kind of thing. So it's quite interesting because this one we cannot see from our naked eye, right? So we have to use a very special tools to monitor this. So these are some of the award that we got, and then some corner, we call it Malaysia Japan corner. We put all the article that we jointly publish with the Japanese university, and we put all the photo that we send our students for the research collaboration. Dr. Teguh is also one of the Japanese graduates. So she know a lot about this Japanese culture. And so we have this, see all the tools here that we have, and we allow the student to operate the tools here, so that by having students have this opportunity to operate the tools, so that we do the training for the student as well. So the student can put in their CV that they are capable of operating like AFM, for example. They are capable of operating scanning electron microscope. So this will be a good value for the student to secure a job in the semiconductor industry. So that's why we give the student, we allow the student to hands-on operate the machine. Of course, the disadvantage is that sometimes we have a problem where the student broke the tools, and do some damage, and then we have to bear the cost. That is very hard for us. So normally we try to keep them trained lah. So we have somebody to monitor. Most likely like a master or PhD student will monitor the undergraduate student. So the senior will monitor the junior students. And then these are the machine, sputtering machine, where we produce the plasma. So for the thin film application, so it's quite the right hand one is on the chamber. So and the left is the controller.
It's very, very expensive, yes?
Yeah, this one is cost like ringgit Malaysia is 1 million. So US dollar is around 300 like 300,000 US dollar. So something like that. So it's expensive, but I think most of the students can use benefit from it. So in order to understand the sputtering plasma, so we have these tools. We have the Langmuir probe. I think in last class I did discuss about this. Langmuir probe, one of the tools that we can diagnose the plasma. So we can use it to study the plasma potential, plasma density, and electron density. Electron is also called as plasma density. We can also capture what is the electron temperature inside the plasma. So this is how it look inside the chamber. So the Langmuir probe is this needle that we can inject into the plasma. So the target is here. We have two targets on the left and on the right. So basically we can do the compound material. For example, we want to fabricate titanium nitride or titanium aluminum nitride thin film, for example. So we can use that. This one, we can put titanium material on the left, aluminum on the right. So then we can create titanium and aluminum compound on our substrate. Just a quick info. So we also got a lot of funding from the local. We have in Malaysia, we call it Collaborative Research in Engineering and Science Technology. So we call it CRES. So which is the one of the government agency that fund all the E&E sector in Malaysia. So we got this amount of fund. So this fund we allocate to create. We have the project title is development of highly ionized physical plasma system for control 3,5 compound thin film. So the objective, we fabricate a thin film for UV LED. So we use a plasma. So we use a plasma for UV LED application. So we got this kind of fund. So this is the picture of the plasma that we created through this fund. So this is the first actually in Malaysia, where we modified our conventional magnetron sputtering system with this high power impulse. So then, so that's why we call it a HIPIMS. So the advantage of HIPIM is that it can create a very high dense thin film deposition. So this is you can see the figure. So on the left is the conventional one. So on the right, you can see a very dense, a very compact thin film, right? So this is the advantage. So instead of having a crack, something like this, so you can have a very good and smooth surface, which is better. Yeah, which is better for our application. So, and then we also collaborate with the industry. Like I think in Indonesia, they also have this company like Symptomer. I think this is a rubber, synthetic rubber company. So they create a hand glove, this rubber glove. I think nowadays this company is gain a lot of profit during this COVID situations. So I think, and then what are the issue that they have is that they have this bubble inside the hand, the glove, the rubber. So where this bubble is not good, they call it as the contamination. So they need us to observe what are the source of contamination inside that glove. So we need a nanoscale. characterization. So we will do the nanoscale detection of the contamination of the globe. You can see the the white dot over here. So these are the contamination. So very small scale, you see the down here is 1 micrometer. So maybe the size of this dot is less than 1 micrometer, maybe around 0.1, 0.2 micrometer, right? So, and then we also collaborate with the vacuum company. So they want to study the roughness of the vacuum chamber. So we use the tools that call atomic force microscope. So we can do that. And then we also collaborate with the company ST Microelectronic. In collaboration with the Malaysian Productivity Corporation, we got a research fund where we produce this atmospheric pressure plasma jet for the contamination removal. So ST Microelectronic is the microelectronic company that create electronic product. It's the IC chip. They do the packaging. So once they do the packaging, there is a metal pad or to create arm for the chips. So that one is created by aluminium. So when they want to do the deposition on top of that, sometimes they have the issue of contamination. So most of the time they use the oxygen plasma for the cleaning. Of course, that oxygen plasma in a vacuum chamber, very big vacuum chamber. So what we do here is that we propose this atmospheric pressure plasma jet. I think Dr. Teguh is one of the expert of this atmospheric pressure plasma jet. So we can use this atmospheric pressure, which is much cheaper for the removal of the contamination. So then we also collaborate with in Malaysia. We have this National Graphene Action Plan. So we have our own company in Malaysia, Preston Geochem. This is we call is a subsidiary company from our university. So collaborate with this National Graphene Action Plan. We can, this Nano Malaysia. So under this Nano Malaysia, they have this action plan. So we create E. coli bacteria sensor using a graphene. So graphene is a new material. Huh? If you guys study about nanotechnology, I think you know about graphene. New material, very conductive. So it can use, they can improve the sensitivity of the sensor. So this one we use to detect the E. coli inside the water. So they develop it. So that is very good. So this is the overall picture of our research facility. So we call it all under one roof. So comprehensive research environment and facilities. So eco-friendly building. So because our indoor lighting is using the LED, so that's why we call it as eco-friendly. And then we have all the collaborator, active student, postgraduate student, and then these are the tools that I can share with you. Okay, so this is an example of the scanning electron microscope where we can do the nanoscale imaging. So you can see this the example of the output that we can create. We can do also the coloring, so more attractive. So this tool itself, I think, cost us right 2.4 million ringgit. So almost 800,000 US dollar. Okay, so this is a sputtering plasma that we have in the lab. So this is the example. Just now I showed the inside the chamber, we have the two target on the left and on the right. So you can see that when we put one target on the left, in this case is we use a zinc as our sputter target. So we can create this bluish color metallic mode of plasma. So where we use argon gas for discharge, and then we add oxygen into the chamber. So you can see the color of the plasma change from bluish to purple. So from a metallic mode to a dielectric mode because of the oxygen that we put inside the chamber. So this is how we can study. I think this one I did discuss last week, where we use the Lamio probe analysis to capture the electron density and the ion density here. So just an overview about it. And then we have this OAS measurement to capture the emission from the plasma. So because we can see here, the color is different, right? So when the color is different, we mean that we can capture some information about from this. So we use the optical emission spectroscopy technique to capture this one. We change the target to a copper, and then we have oxygen and argon flow so that we can create a thin film CuO. So this is the result, where we can see when we change the flow of the oxygen, so we can see that the intensity is changing. So this is a copper emission. So we can select what we want to observe. So in this case, we observe the copper. So meaning when we add too many oxygen to the chamber, the copper cannot release from the target. So in this case, we use the copper as a sputter target. So we capture it over here. So of course, so you can see the copper intensity is changing based on the power supply, based on the oxygen flow rate. So this is how we can monitor or control our chamber. So these are the list of the tools that we have. RIE, FISM, AFM, I think, okay. Okay, this is about this atmospheric pressure plasma characterization tools. So where we create our own plasma discharge. This one is using atmospheric pressure. So it's very simple. We have a needle inside a glass tube, a quartz glass tube. And then we use a neon power transformer. So this power supply can give a very high voltage at high frequency. So this is very cheap one. We just bought it using the Alibaba from China. So most likely that power supply is used for the neon light. If you go to the shop at night, we can see a lot of neon signage at the shop. So that is the same power supply that we use. We supply to the electrode inside, and then at the outside is so it's grounded, I think. And then we put the gas, argon, and then we have some current probe, high voltage probe. Sorry, this one is also powered. So both electrode is powered, and then we can create the discharge, something like this. So this is very small. Actually, it's just like a needle, a size of your this small hand, a small finger, right? So quite small one. So we can use this one for the treatment. So this is an example where we can use this plasma jet to treat the E. coli bacteria. So we collect the wastewater and we spray it into sterile in some petri dish, and then we incubate it. So meaning that we just grow it. We just try to make sure the bacteria grow, and then we can observe it. Okay, so inside the petri dish, we do the treatment. Okay, we try to observe, like for example, this example, we have two gaps, which is 1.5 centimeter and 2.0 centimeter. So one on the left is that we touch, so the plasma will directly contact with the water, and then on the right, the plasma didn't contact with the water, so we can see the difference. So this is the example how we can see the plasma can kill the bacteria. So on the left, upper left is a control sample. You can see a lot of bacteria inside here. So when we treat with the plasma at 10 seconds, we can see the plasma, the bacteria reduce. 20 seconds, you can see reduce a little bit more. 40 seconds, 60 seconds, and 80 seconds, we can see almost complete inactivation of E. coli bacteria. So the survival of E. coli bacteria several seconds after the plasma treatment. So very quick, very fast one. So which is very interesting. Okay. And then we also try this plasma for the fabric. So in Indonesia, in Malaysia, we have a silk, we have a batik, we have a lot of fabric, right? So we can use this plasma for the treatment of the fabric. So example here, we have a cotton. Before we do the treatment, you can see this is a water contact angle analysis. We call it water. So we drop a water, then we see what is the angle that we can get when the water drop on our fabric. So for example, this is the cotton. So it not absorb water, but it a little bit halfly is absorb the water, right? So you can see the structure of the water drop is like this. When we expose to the plasma, and then we drop the water again, so we can see all the water abolish is very clear. No more hemisphere structure like this. So we can see that after the exposure, the fabric absorb the water and become hydrophilic, so smooth, so it will absorb. So this is very interesting. So where we can alter the property of the fabric. So another fabric that we use, lycra. So you can see before we do the treatment, it can have a very hydrophobic. Okay. So when we do the treatment completely, so it become a hydrophilic. So this is advantage. We can use plasma for the treatment application. So this is I think one are the tools on plasma that we have in our lab. Just to share. Okay, I share another slide. Let me unshare first. Okay, is it clear? Any questions?
Ya,
So,
silakan kalau ada pertanyaan.
I invite everyone if you want maybe when the border is open, if you want to come to our university, see our facility, so you are most welcome. Okay, so then I put.
Is there any master scholarship there, Professor Nafarizal?
Yes,
Available?
yes. We offer a master scholarship here. We give the allowance master and PhD actually. So we give allowance 1,000 ringgit per month for the students. So of course, it depends on the selection, but up to now, we still can offer like 100% lah. Student that join us full time can get this scholarship. So 1,000 ringgit per month, living here in Parit Raja area is enough lah. Because cost of living here, I think student may need like 600 ringgit per month, something like that. But of course, the fees, the student have to bear the tuition fees lah every semester, right? So every semester is like, I think 1,000 ringgit almost.
So the scholarship also covering the tuition fee?
The scholarship don't cover the tuition fee. It's just the allowance, monthly allowance for the cost of living.
But they still can save money per month, yes?
Yes. That's why the cost of living is like 700. So you can save every month 300 ringgit. So you can use it for the tuition fees. Something like that.
So maybe there is an available information for next week or for next term enrollment, university enrollment. Maybe please give the information Professor
Okay.
Nafarizal, maybe student have interest to continue their study there.
Okay, sure. I will share that.
Okay, thank you.
So most of the student here is the final year student.
Kalian semester berapa sih? Saya nggak- So in which grade? All of you guys? For grade atau some there is my student actually ya, Leni. Oh no, nggak ada Leni ya. Saya tuh bingung sama kelas satunya lagi nih. So you all belong to the third grade, Karisma dan kawan-kawan? Tahun ketiga ya? Atau tahun keempat?
Yes.
Oh, sebagian ada yang tahun keempat ya? Kayak Rahmat begini nih kan tahun keempat ya?
Iya, Bu.
So part of the student is now in the fourth grade, a 4 year, yeah, and then another the third grade. So semester berapa ya kalian ya? Kalau third itu 5 ya, 5th semester ya,
Iya, Bu.
and also 7th semester. Yeah. So part of the student in the last year, Professor Nafarizal.
Okay, so that's very good. Okay. So I will pass the information later so that maybe if you guys
Okay.
because I think last month we got the student from from Brawijaya, I think.
Oh,
So-
for undergraduate or for
No,
master?
continue for the master. So she did came here for the final year project. So it's like a final year attachment. So to conduct the experiment here, so she stay with us like 1 month last time during the undergraduate. And then after she finished her undergraduate, now she came back as a master student.
Okay.
So she registered last month, I think, because she came to university and then do the self quarantine at home. And then when everything, because she already got the vaccination, so then that's why she can come to here. So then now she joined the lab. Later I can consult. Maybe she can give some info as well. Okay, so I continue on the this is the slide. I call it the title of this slide is a thin film coating using a PVD technique and its diagnostic. So I did discuss already on the diagnostic. So I will just continue on the part.
One of the example, yes,
Yep.
for the plasma diagnostic and PVD technique.
Okay, so right. I'm not sure any one of you have ever seen this before. This is a very old technology. Oops, I want to. How can I wait? I want to make it larger. All right. Karisma, have you ever seen this before?
Karisma itu angkatan milenial ya. Have you ever seen this before, Karisma?
No, Prof.
No.
No, so this, you know, what is the purpose of this one? What this one? Can you guess? For what purpose?
Do you know what this is, Karima?
Tape.
It's a tape.
For radio.
Yes, it's a cassette tape to listen to the song. So one cassette tape can have like 10 to 15 song like that. And then we always have a problem with this one. So where the tape go hell wire, something like this. So we need to use the pen. Use the
Yes.
pen to pull to swing it and then to make it at a proper position. and so that the tape can pull in. So it was the technology that I think most of you haven't have this opportunity. So we use that to listen to the song, and then the technology changed from this cassette tape to a CD. And then in Japan, they have another one they call MD, mini disc, and then we have the the USB thumb drive. So the same technology is changing from a hard disk. This is the hard disk that we use quite long hour, and then the hard disk that we use mechanically. I think this one is mechanically. And we have a bulky laptop. For example, before this, we have a very bulky laptop because of this hard disk. So this hard disk is store the memory, whatever file you want to store, which is it will be inside this hard disk. And then the technology changed from this hard disk to a solid state, so solid state drive, so SSD. Nowadays, I think handphone, tablets, even the laptops nowadays they are using this SSD technology, so which is very much smaller. So it's something like this. So you just have a chip. So you don't have this disk anymore. You don't have this arm of where this arm actually the reader, they read the content inside this disk. So this is mechanically moving. So that's why when we change from a hard disk to a SSD, so we can read faster for our computer. So our computer can move faster. So by having this solid state drive, so we can also have a very good handphone nowadays. Okay, so we can have a lot of memory on our handphone. So we can do a lot of calculation. When I mean calculation, we can do a lot of process. We can use our handphone for the camera. We can use our handphone for the video call, for the WhatsApp, for the internet. So we can do a lot of things with one handphone nowadays. So 10 years ago, handphone can only be used to call for the communications. So nowadays we can use it for, even we can do a job. If you have a very big handphone, you can use it with a PowerPoint. You can use it for the TikTok, many things, right? So that's why the technology evolved because of this thin film technology. So this is the keyword here. So where we have a thin film technology, so under this thin film, what we do is that we inside our chip, so there is a very, very fine nanostructure, nano thin film. So this is the example where we have a silicon substrate. So we have a gate, we have a control gate. All these are transistors. So inside the chip. So this transistor is created by this thin film technology. Okay, so this is the background. So some outline. Okay. So to create a thin film, we need a coating process. So under the coating process, there are several scope. So on the left is the gas phase, so where the plasma come in. So then we can also have a molten particle, so a thermal spray process like this. So we can have also the chemical process. So you can just have a bath, like a bathtub, and then we put all inside that bath. And then we have also the like the welding process. So this is also solid particle sintering. So this is called. So on our scope for the plasma, so we focus on the gas phase. So where we use a technique called CVD, which is chemical vapor deposition, and also PVD, physical vapor deposition. Okay. So for chemical vapor depositions, we have a chemical reaction between the gases and the heated substrate and resulting deposition of thin film on the substrates. So what we have here, we have a gas, a precursor of gas, for example, a nitrogen, CH4, methane here, and then we have a reactor. So inside that reactor, after we put the gas inside this reactor, we apply the energy to make sure that you get some heat, you get some chemical reaction, you get some process inside here. So it can be a resistive heating, it can be a inductive heating, it can be a plasma enhanced process. So by having this energy source, so we can create a chemical reaction. So where the output of this precursor, so we can get a thin film. For example, we can have a diamond or graphite carbon base. So we can also have titanium nitride. We can also then during the process we can have a byproduct. For example, we can have a gas phase product like hydrogen like this. So these are the byproduct that we can get. So this is we call chemical vapor deposition. You use the chemical reaction, do the treatment, and then we got the thin films. Okay, this is the chamber. This is most of the time the CVD consists of this reaction chamber, substrate holder, reactant, whether the source and the carrier, and then the exhaust. We have the vacuum pumping system, and then activation source, and also substrate heater. So this is the example, the cross section. So we have a chamber reactor here. So the gas is like here. So we flow all the gases inside the chamber. So we have the induction coil inside here. You can see we will circle around the chamber, and then we supply the power supply, for example, AC voltage to heat the chamber. Then we get the energy. So then that energy will make the reactant gas reactive, and then it will deposit on the substrate, because most of the time the substrate is cooler compared to the environment, so it will deposit on the cooler side. So that is the reaction. And then to make sure the chamber is a vacuum, so we have the vacuum pumping system like here. So then we can have a good process here. So most of the time we need a vacuum in order to make sure that the environment is clean, no contamination, so that the chemical reaction will occur as what we want. So if we don't make a vacuum inside here, so maybe we can have many oxygen, many nitrogen inside here, so which is unnecessary process. Sometimes we don't need. So that's why we have to make sure it's vacuum. So this is one example of a CVD process. It's much cheaper way. So where we have a alumina board and a glass substrate, and this is a glass ceramic tube. I think it's a big one. It's a ceramic tube. And then we have a carrier gas on the one side, and then the pumping on the other side. And then we put inside the oven, so that inside this alumina board, we put a powder. That powder will evaporate and then will deposit on this glass substrate, a very thin one. So that's how you can see after we do the process, 1 hour, 2 hour, 3 hour, for example, we can see we can characterize the thin film that we grow on the glass substrate. This is the example of titanium dioxide. So created by my colleague, Dr. Zainizan and Dr. Hairul. So this is example, simple CVD process that we can have in our lab. And then compared to the chemical vapor deposition, we also have physical vapor deposition. In short, we call it as a PVD. So PVD is where we heat the transfer in evaporation, provide the transfer of vapor atom or molecule from the target to the substrates. So CVD, we have a chemical reaction. So that chemical reaction create the thin film. But PVD, we do a physical process. So where, for example, we give a heat to the material, and that material itself will eject or evaporate. Okay, that we call evaporator. So what we still need, we need the gas for the discharge. We need the gas for reaction if necessary, and then we need the material, the raw material, the coating material that we want to use, and then we put inside the reactor, and then we supply with the energy. We can get the thin film. Okay, this is the example. On the right is the where they want to coat the drill. This is the, if you see at the bottom here, is the drilling head. Okay, the drilling head. We want to coat with hard coating. So most of the drilling head is made of the steel. So that steel, sometimes when you use the drilling for quite a long time, so the drill is not good anymore. So that's why, in order to make sure that the lifetime of that drilling head longer, so we have to do the coating of hard coating, we call it. So hard coating is most of the time they use the material like titanium nitride, titanium aluminum nitride, for example. So we put the drill head inside the chamber. We create the discharge of titanium sputter source here, and then we add the nitrogen and the argon environment here, so that we can create the titanium nitride coating. So most of the time in for PVD, it's also, we call it as a sputtering. Of course, there is also other PVD process like evaporator, laser ablation. So, but I just want to share here is on the sputtering deposition. So what is sputtering? Sputtering is a process of yielding atom or molecules of target material through a constant bombardment of the target material surface by the radical ion in the gaseous plasma. So as mentioned, in a plasma, we have ion, we have free electrons, we have atoms. And the most important one for the sputtering is the ions. So in the case, we use argon, for example, for the in the sputtering. I think last time we put argon. Okay, we put argon most of the time. Argon gas inside the chamber. So this argon gas will create the argon ions. So that argon ion will actually be in here, inside this one. So that argon ion will have since it is an ion, it will have a directionality when we put the negative bias. So this is the electrode. We can bias it with the negative charge. So that when is negatively biased, so the argon ion will bombard. We hit the target, and then this target material will get released out. So this is the process of sputtering. So it's like when we play a billiard, snooker. So we have one ball to hit another ball, and then that another ball will spread around. So that's the situation happening. So we have argon ion, a very energetic one, because it is ion. So we supply with a negative voltage to the target, and then the ion will hit the target, and then by hitting the target, we release the atom from the target. So this is called a process of sputtering. So this is the example. We can see ion hit the target. So what will happen when it hit the target? It will release a secondary electron. It will release it will do a gas desorption. It will do ion implantation. So these are the phenomena that will occur when the argon hit the target. So the most important part is that the sputtered particles. So the particle will release away from the target. So then where it go? So where the sputtered particle go, it will deposit on the other side. So that's how we can create a thin film actually. Okay. Okay. This is one project that what we did. We study about the self-sputtering effect of the inside the plasma. So as I mentioned, inside the plasma we have this okay. So inside this plasma we have our target. We have also the atom and the ions that we hit the target. In this case, we use a titanium as the source of target, and then the ion will hit the titanium, and then we release the titanium atom. So in some cases, we not only have a titanium atom, we can also have titanium ion. So this ion actually is not, sometimes it's not good, because on the other side, we try to create this thin film. So where the atom that release here go to the substrate and create a thin film. So this thin film sometimes will get damaged because of the ion bombardment. So even though that we want to do the sputtering process on the top, but sometimes because of the balance of ion that have at the down here, so this kind of ion will damage the thin film through this ion bombardment process. So that's why we have to study how this phenomena occur at the bottom here. Okay, so and sorry, this one is. Okay, this is one free software. If you guys can try to explore. If you want to study about the plasma and the mechanism, physical sputtering mechanism. So it's a free software. It's called as a TRIM simulation. So this TRIM simulation is a free software. You can download it and you can try simulate. So for example, in this case, we try simulate. We use the argon gas. So we select the argon gas and then we select what are the target that we want to hit, and then we can run it and then we can see example result here. Okay, so this is the example about how the ion bombard on the titanium target. So this is where we have the titanium target here. So the ion will bombard from the left to the right. So it will penetrate inside the titanium material. So this is to show, for example, when you have an argon ion at 100 eV, this is the argon ion track in red, and then the green is the titanium atom. So you can see the argon ion will hit and then will penetrate inside the titanium. When we enlarge the argon ion energy, so we can see how the argon ion can go inside the titanium even deeper. Okay, so then we try to modify. Instead of using argon ion, what if we use a titanium ion? What's the difference? So we can see when we change from argon ion to titanium ion, we can see the trend is almost the same. So we can see the trend, the length, the scale of the depth of penetration is almost the same, even though when we increase up to 800 eV. Okay, So the conclusion here, the collision cascade of argon and titanium inside the titanium target is almost the same. So meaning that it can show the effect of the self-sputtering inside this process. So this is the result to show that the sputtering yield of titanium. Sputtering yield is a number where we try to understand when one ion hit the target, how many ion that will be, how many atom that will be released. Okay, that's why you see the unit is titanium atom per ion. So one ion hit the target, how many atom released? If the sputtering yield is 1, meaning that one ion hit, one atom release. If the sputtering yield is 0.5, meaning that one ion hit, nobody released yet. Second ion hit, then will get released because the sputtering yield is 0.5. Okay, if the sputtering yield is 2, meaning that one ion hit, 2 atom release. Okay, this is what we call as a sputtering yield. So using this tool, we can evaluate the sputtering yield. So you can see the sputtering yield from the argon ion and the titanium ion is not much difference. So we can conclude that the ion bombardment damage is both coming from both elements, which is the argon ion and the titanium ion here. So this is our conclusion on this part. So it's a free software. I think you guys, if you want to explore, you can try to explore, try to download. It's a free software, so you can download and try to play around with that software. I think which is very good. It's good. You can put into your CV if you want to go for the interview in the semiconductor industry. Right? So I think it's good. Okay, so then okay, we also use a sputtering plasma system to deposit a thin film for the solar cell application. Okay, the background of this study, so we can see this is the top 10 problem for the next 50 years in the world. So number 1 on the energy. So number 2 on the water, number 3 on the food, number 4 on the environment, and then number 5 in the poverty. So these are the issue that the world or the human that need to solve, right? So I think it's very hard to find people that we live without a source of energy, right? So we can see in the rural area, they try to create a solar panel so that they can have their own power supply at home. So that's why I think this top 5 issue that we have to solve. So this is Malaysia at night. You can see, let's see if we can. So here is Kuala Lumpur. Here is what? Do you think what area is this?
Jakarta, yeah.
Yeah, I think it's Jakarta, right?
Yes.
So Indonesia, Jakarta. So maybe somewhere here is
Surabaya.
Surabaya. So the most, I think at night, you can see a lot of light used here. So down here is Singapore. Okay, so a lot of energy actually is used at night. So even though it can see from the sky. So this is the satellite image. So we use a lot of energy. So that's why I think we have to be cautious in that. Okay, example. For YouTube user upload 72 hours of new video every minute. Every minute we have 72 hours of video. Okay, Skype user connect 33 million hours per day. Google receive 4 million search every minute. 4 million search every minute. So one Google search will take like 1 kilojoule of energy, which is equivalent to one AAA battery. So you can see a lot of energy. And then this year, this is 2017. To 22% of the energy in the USA is consumed by their data center. So their data center may be like the Facebook data center, the Google data center. A lot of heat is used over there. So we use a lot of energy actually in this world. So how we can maintain this for our next generation? So this is a very big issue. So are we still capable of having a lot of petroleum? Do we have a lot of petroleum to produce more oil? So that's why I think most of the country, we are moving into this kind of solar panel, renewable energy. So I think Indonesia also moving into this part. So this is where some area in Negeri Sembilan, where they have this solar farm, like 6,000 megawatt. So it can cater up to 7,000 homes. So the technology in this solar cell is very important. So there is a roadmap by United States. This is published by National Renewable Energy Laboratory, NREL. So where they study about how to improve the efficiency of the solar panel. Of course, when we see the solar panel, the energy that heat, the light, the sun that heat the solar panel is not 100% convert into the electricity. So this is what we call as the energy efficiency. So when the light hit the panel, how much it convert to the electricity? So this is the graph to show the trend. So we call it as efficiency. So the trend, we can see the trend like this is quite an old version, 2015. Actually, you can download the latest one in the NREL website. So, but what I want to say is that most of the technology is up to like 40%, 50% of efficiency. That is the lab scale technology. The one that we have in the market, the most of it is based on the silicon solar cell. So it will be in this range, 40%, 50%, 30%, something like that. So that is and then of course the efficiency will drop every year. So when you use the solar panel a lot, then the efficiency will keep drop. And also the efficiency will drop when you have too many cloud. It's cloudy. I think in Southeast Asia we have many cloud, many rainy season. So that also will drop the efficiency. So people around the world is researching, try to explore how they can improve the efficiency of the solar panel. With the CIGS solar cell. This is the material, name of the material. So research in our lab, we try to also explore this kind of thin film solar cells. So we explore this new material, CZTS. So by using a sputtering plasma deposition, so we try to explore this one. So this is the cross section of the materials. Okay, I just want to skip this one. It's not very much important. Okay. And then by having this plasma tool, we can also do the characterization, do the diagnostic. So this is, I think I have discussed previously. Plasma that we call atmospheric pressure plasma, very basic one here. So actually, originally it was developed quite very long time ago, where they produce ozone from the oxygen gas that they have here, and then they put inside here, inside this tube. Helium gases, and then this is dielectric barrier discharge plasma, DBD, and then this is a corona discharge. So you can see the trend. When you put more energy, you can create a more high density, high temperature plasma. If you guys are familiar with the spark plug, or maybe the like if you have a what is called as I think we call when you heat at home, you want to cook, it's also a type of plasma, right? So that gives a very low amount of energy, but if you put many more energy to the heat, you can have a spark plug type of discharge. So that is we call as a plasma. So this is we call as arc discharge at a high temperature and high density. When we do welding, it's also a high temperature plasma. So how this atmospheric pressure plasma is very important very recently because of this research where they try to explore the plasma where you can touch by your hand. You can see the example here. So you can touch it. So meaning that the temperature is low, the voltage is also low. And they can use it for the treatment of the skin. Okay, you can see the example here where the tissue, the control one is on the left, it can get damaged if you don't do any treatment. But on the right, you can see when you do the treatment, it will keep the health of the tissue. So, which is very good. In fact, if you guys are the one that scared about the teeth treatment, okay, so most of the time when we go to the dentist, what they do, they have the drilling, right? They will drill your teeth. So that is the mechanical treatment on the teeth. So now we try to explore this plasma jet. You can see upper left here. So we can do the treatment using the plasma jet. This they expose the plasma. You can see on the right is the area that we expose to the plasma, which is very murky. So you can see the left without the treatment, on the right is with the treatment. Also kill the bacteria, can do a lot of process. So what do they have in this atmospheric pressure plasma? They have the UV light, they have the visible light, they have the reactive species, they have a charged particle, they have some thermal radiation, they have electromagnetic field. So a lot of complex mechanism occur here. So that help to the use of this atmospheric pressure plasma. So we can see this atmospheric pressure plasma can be used for wound healing. If you have a scar, you have a blood coagulation, clotting of the blood. You can use it for the air and water treatment. You can use it for the cancer therapy. Nowadays, they are trying to do this one. And they can use it for the surface treatment and modification. They can use it for tooth whitening and many more. So you can see we can explore this plasma for a lot of application. This is the picture of how we create our plasma. So you can see this one that we bought from Alibaba from China. I think it costs like 20 ringgit, something like that. You see like 1,000. Yeah, it's like 1,000 rupiah, something like that. Quite cheap one. And then the glass tube that we have here, the outer electrode, the inner electrode, and then we create the discharge. You can see here. So, okay, this is the same one that I explained just now about how we can do the treatment on the E. coli. So in a minute, we can do the inactivation of the bacteria, so which is very good. So if we put it far, you can see the bacteria is still there. So we can have a 100 count of bacteria here. So meaning that it's better to do the direct contact treatment on the water. So we did characterize, so whether the heat treatment that kill the bacteria or what. So this is how we capture the temperature. So at 3 point, for example, so we can see the temperature is high on this one, on this part, but the temperature here is not that high, which is this one on the sample. So to conclude this one, that we conclude that the heat treatment is not the one that kill the bacteria, but we use the OES, optical emission spectroscopy, to characterize the plasma. Again, what we can see here is that at the outer of the plasma needle, we can see this UV region, UV emission. So we can conclude that this UV emission is the one that killed the bacteria. So the cost of plasma needle is very cheap. It's like 300 ringgit here. So it's like 1 juta, 1 juta rupiah, 1 juta rupiah, something like that. So, which is very good. So atmospheric pressure plasma can be used as an innovative and promising technique for a super fast treatment technology. So the issue and challenges: feasible plasma reactor configuration for practical use, cost and lifetime of the plasma power supply, the change of the physical and chemical property of the treatment, and then we need to scale up the technology. So as a summary, I can conclude PVD, physical vapor deposition technique using magnetron sputtering, can be used to deposit this thin film. We need a smart plasma diagnostic technique. And then we can see that how atmospheric pressure plasma jet can be used to inactivate the E. coli bacteria. So actually what is a bad thing about E. coli bacteria? It will give us a stomach problem, actually, the E. coli bacteria. So when you get this E. coli bacteria, you can get a lot of diarrhea. So which is not very good. So most of the time, E. coli bacteria is inside the water. So that's why this E. coli bacteria is very dangerous, that we need to kill or inactivate it. So that's all for this slide. Is there any questions?
Yeah, any question from students, please? Hafid Nur mungkin ada pertanyaan, Hafid?
Saya belum ada, Bu.
Belum ada.
I have a question, Prof. Nafarizal.
Yes.
It's very interesting when you present about the sputtering for deposition titanium nitride or others, yes, using titanium target. So you compare using argon ion and also titanium ion.
Yes.
So the titanium ion, I mean if using argon ions, so it's coming from the argon gas, right? So
Yes.
when you use the titanium ion, so what's for the source?
The source of the titanium ion is actually the sputtered atom. It will do the electron impact ionization so that the atom itself ionized inside the plasma. So after it's sputtered away from the target, because of the free electron that we have inside the chamber, that Ti will react with the E and then do the ionization. So Ti become Ti plus.
So means the titanium ion is coming from the target, yes.
The target itself, yes. So of course, the density of titanium ion, if we compare the argon ion density, is very much lower lah.
Yes,
Less lah. It's less lah. Because of we didn't put.
But the impact is similar, yes. When
the impact is similar, so we study about the impact, not on the the density.
I thought you add more of titanium ion, so it's coming from the target itself.
Yeah, it's coming from the target. So so it should be less impact on the. I'm not sure. So the density is maybe 1 order or 2 order of magnitude lower lah, less than argon.
Okay, very interesting.
Yeah. So it's a good software. I think you can download and also try to explore. I think the student can use it for the nowadays. If they cannot do the experiment, they can do that kind of simulation. It's also good, right? So at least they can do simulation at home.
Is it the software is free?
It's free software.
Oh, I see.
Yeah.
So what the name of the software?
TRIM, TRIM.
Okay, TRIMS. Okay.
Yes. And you can select a lot of element, not only argon. You can use it like helium, xenon. You can also put like zinc, many elements that we can choose. So we can play around with that materials. Yeah.
Okay. Dr. Nafarizal, I have a more question about in atmospheric pressure plasma jet. So have you has data comparing using and without the magnetic field?
Oh, we didn't have that kind of information. You mean the magnetic field inside the plasma?
Because you know that the plasma itself can be influenced by the external magnetic field, right? So in the atmospheric plasma jet, so maybe did you have ever make a treatment with or without the magnet could be placed anywhere, maybe in the bottom or the up, because we don't have explored it yet.
Yeah. So I never tried that. I never. So is there some article that's showing that there's some effect? Of course, when we put the magnetic field, it will diverse or change the movement of the atom and ion inside there, right?
Yeah, that's why I'm curious. How about if the magnetic field is upper or in the bottom of the sample or in the middle or others, because we haven't explored.
Yes.
But no, not yet. Yes, not yet explored in your lab also.
We never put any magnetic external magnetic field to the plasma. But very good suggestion. So maybe we can try to explore on that. It's a permanent, we can put the permanent magnet lah kan. It's not
Yes,
the
magnet bar only.
magnet bar, right?
Mhm. So student, any questions from you?
Or I should ask.
Yeah. Also, good. So Professor Nafarizal, if you want to ask the student, of course, very welcome.
No,
Kan gitu ya?
I'm just joking. But I maybe try to create because I need to do some evaluation on the student as well, right?
Yeah. Examination.
Yeah, so
Nilai lah ya, nilai. Great.
so I will try to create a question. I post it in the WhatsApp group, and then they will submit in a Google form. Can I do like that?
Okay, that will be great. So yeah, Charisma also when the class at the beginning class also asked me about the examination from Professor Nafarizal or how it will be and others. So by Google form, yes, Professor Nafarizal.
Yeah, I will create a question, and then I post it into the WhatsApp group, and then I will give like 1 day. It can be like that, or I need to consult with you to go on how we can.
Possible. That's okay.
Possible,
Yeah, okay. But I don't know in only 1 day gimana mahasiswa semua ya. Kalau 1 hari gimana?
Yeah, okay. 1 or 2 days
maybe
lah.
they need more to.
Okay.
So kecuali kalau unless if the examination is take a place in the Wednesday and in the same of the lecturing day.
Okay.
So they have time on that. For example, Wednesday on the 10, 11, 15, maybe they can make it 1/2 hour. But on the other day, I don't know, they maybe have another schedule. So maybe, yeah.
Okay, I will.
I mean the deadline. Yes.
Yeah, the deadline. I think. Okay, right. I will just choose the deadline later lah. Okay. Maybe I see the how the scale of the question first lah. How difficult or not the question. So then we see on how the time. What's the time appropriate time to give lah.
Yes.
Okay. So I think that's good.
Ada pertanyaan lagi, Karisma? Terutama especially on the examination. It's already clear?
Belum ada, Bu.
Sudah ya? Oke.
Okay.
Okay, just a quick one. Maybe I just want to show this one. I just got this from the internet about how you can understand the vacuum technology. So I will share inside the group. I think I put inside the folder lah, the folder that I want to share, the Google folder, right? Google Drive folder. So about the vacuum system, how important is the vacuum? What is the meaning of vacuum? Example here, we have a chamber. So the vacuum is we have a lot of particles inside the chamber, right? So we can consider the vacuum from the free parts. So how many, when the particle move from one point to another point, it will hit another atom or not. So that is what we call as a pressure, right? So the ideal gas law we call as P equal NKT. I think everybody here is much more expert in this. So when the pressure is at low vacuum, so which is 10 to the power of 3 until 1 millibar. So the number of density is like this number, 10 to the power of 16 particle, the number of particle. So quite very large amount of particle. So this is low vacuum. High vacuum, ultra high vacuum, extreme high vacuum. So these are the value of this vacuum, right? So the pressure range is 10 to the power of 12, and we have only like 10,000 particles. Right? So this is extremely high vacuum. So it's very difficult to create a high vacuum. But anyway, when you have a high vacuum, the particle mean free path. This is another number to consider about the vacuum condition. So mean free path is meaning that how far the distance that the one particle can go before it hit another particle. So this is what we call mean free path. So if the mean free path is longer, meaning that it will move freely without hitting anybody. Right. So that's why for a high vacuum, extremely high vacuum, the mean free path is very high, 10 to the power of 8 centimeter. So it can travel many way and then without hitting anyone. So nobody, no particle. So it's very high vacuum. So this is a good one. I think the value that we need to understand. And then we also need to understand in a vacuum, what is actually we evaluate inside a vacuum is throughput. So the throughput is come from the conductance and the pressure difference. So pressure P1 and P2. So if P1 is larger than P2, there will be the gas flow. And then the C is conductance. You can calculate it whether in a series condition or maybe in a parallel condition. So the pressure is in unit of millibar. Conductance is in unit of liter per second. Throughput of the system is the Q is in unit of millibar times liter per second. So this how we calculate the chamber, this is our pump lah, our pumping system, throughput of the pumping system. So this example how they calculate the conductance with orifice or with a tube. A tube is a glass tube lah, it's panjang punya tube, for example. Or orifice is a small needle lah, orifice small needle, small hole. So if the orifice structure, so the conductance C can be calculated from here. If the tube, so the conductance C can be calculated from these equations. Okay, so then we can use this C, C here. So this is another software. I think they can do the simulation of the particle. Just I want to share is that how we can evaluate the pressure inside the chamber here. For example, here the pressure 1, chamber 1 and pressure chamber 2. So what we need is a low vacuum. Okay, so how we can increase to lower the pressure inside the chamber? There are two approaches. So number one, we reduce the Q, the throughput here. How we can reduce it? So we can use the chamber, a small chamber. Okay, so if we use a small chamber, of course we can have a very high pressure, lower the high vacuum, lower the pressure, meaning they have a high vacuum. So if we have a small chamber, we can create a very high vacuum, or we can increase the speed of pumping, as efficient, so effective, and this is the effective speed at this position. So where you have a pumping here, so this pumping have their own speed, but of course since we have a conductance inside this region here, so there is some effective speed here. Is calculated from the this equation lah. Okay, so this is the example. You can see the effect of the size of the chamber, and also how we can see the effective speed of the chamber. So this example where you have a very big chamber here with this small pumping here. So how do you think is it effective? So This some question I think is very interesting to show that the pumping system for anybody who want to create plasma, we need a vacuum pumping, we need a vacuum system. So that's how we have to consider about the vacuum system. So this is an example where you have they create this is vacuum chamber. They can connect it to several type of pumping. I think this one is not important. What is more important is on this type. So we need to understand what type of pumping that we need in order to achieve the pressure or the vacuum that we want. Example, if you need a ultra high vacuum, we need this kind of diffusion pump. Okay. So if you need a high vacuum, this kind of pumping can also cater. So we have a turbo molecular pump. Sorry. So this high vacuum is covered by this pump. The titanium ion pump here, the sputter ion pump here, cryogenic pump here, and turbomolecular pump here. So it will cover ultra high vacuum and high vacuum. So this is the pumping system that you have to maybe try to explore lah. Okay. So and then for a rough and medium pump, so we call a mechanical pump and a diffusion pump. Most of the time we use this mechanical pump. So this is a pump that very basic one that we can use it to create a vacuum. So this one is not that expensive lah, maybe like 20,000 ringgit Malaysia, something like that lah. So but the turbo molecular pump, this all the cryogenic pump, sputter ion pump is a complex pump lah. So which is used in the industry, semiconductor industry. Okay, so after the pumping system, we need to measure the pressure as well. What is the pressure inside there? So these are the tools that you need to familiar with. So like a manometer here, I think this one quite easily you can see when balloon. They want to fill in the volume, so they use this kind of a Borden manometer. We have also the Pirani gauge. This is also very cheap one. You can monitor at the rough vacuum region. And then if you go to high vacuum or ultra high vacuum, we need this kind of tools. Penning gauge, hot cathode, cold cathode, extract gauge, and RGA. So these are the more advanced tools. So just to make sure that everybody here familiar with this term. Okay, you can see this very big chamber. So you can see it's overseas lah. Okay. So you just want to share this final slide with you guys. Okay, that's all I think that I would like to share. Just to make sure that everybody understand about the vacuum, about how we can use it to create a plasma. So we need a vacuum technology. So to create a plasma, we need a vacuum, and then we need energy to supply. And then we can use it for many applications: treatment, teeth treatment, fabric treatment, deposit thin film. So a lot of application. I hope it will be beneficial for everyone here. Okay, I think that's all, Dr. Teguh.
Okay, thank you very much for the very interesting lecturing from the first chapter until to the fourth. Again, from the student, any question? So as conclusion, Professor Nafarizal, I've already summarized that for making plasma, actually for lower or in the low pressure plasma, so the vacuum system is required. And that's why some equipment maybe is needed, yeah. And in Indonesia, maybe it's depending on the institution, maybe. Yes. So for our institution, maybe some of the equipment is very, very expensive to buy. And other is also possible to conduct the plasma in atmospheric pressure. For example, the plasma jet. In the plasma jet, the vacuum chamber, vacuum system is not required, but the energy, yes, Professor, energy, high energy, so it's also needed. Yeah, dari student, from the student, any question? If no, maybe we can close the class. Ada pertanyaan, Karisma dan kawan-kawan?
Dari saya belum ada, Bu.
Belum ada.
Belum ada, Bu.
Ya, nanti mudah-mudahan apa namanya examinasinya mudah ya. I hope the examination will be easy for you guys, and you can submit the answer before deadline. Yeah. Please turn on the camera all, and salah satu perwakilan dari sini, representative student, maybe you can deliver your thank you to Professor Nafarizal. Siapa yang mau memberikan speech? Ya, short speech lah ya. Nah, ada yang mau memberikan? Perwakilan, Pinka? Silakan, Pinka.
Thank you, Prof. Nafarizal, for all the explanation about plasma, and maybe we can study more about plasma in next time.
Okay, you're welcome. So if you guys have any question, just you have my phone number inside the WhatsApp group. I think you can just text me. I'll try to explain. Yeah. So hopefully that I believe my explanation sometimes it's not that easy to understand. so if you guys have any other question, just text. Don't be shy lah.
Ya, jadi jangan malu, takut, atau hesitate ya untuk memberikan pertanyaan. Kalau misalnya ada pertanyaan, silakan kontak di number Profesor Nafarizal yang ada di WhatsApp group. Thank you very much, Professor Nafarizal. I really appreciate your support, your help to conducting together in the team teaching on the plasma chemistry. This plasma field is also, I think, is very new in the chemistry field, I think, yeah. So because maybe part of in talks or discussing the plasma chemistry is very related to the physics and engineering and others disciplines, other field. So I think this will be interesting knowledge, and also benefits, yeah, give you benefits to the student. For the explanation of the plasma delivered directly by Professor Nafarizal, who one of the expert, yeah, in the plasma during in his lab, in his research, from his study and others research experience. Ya, terima kasih Profesor Nafarizal. Yang lainnya mahasiswa, saya ucapkan terima kasih juga yang sudah masih bertahan ya di kelas ini. Mudah-mudahan apa yang sudah kita bicarakan dengan Profesor Nafarizal membantu kalian mengetahui tentang plasma. Mungkin sebagian besar ada banyak bidang lain, fisika, kemudian teknik, engineering ya, tetapi mudah-mudahan bisa dipahami. Thank you very much, Professor Nafarizal, and we will waiting for your post question. For the examination, and I hope the student can deliver or submit the answer before the deadline with the perfect grade, ya, dengan nilai yang bagus ya, mudah-mudahan.
Insyaallah.
Ya, Karisma mohon diambil take foto ya. Nah, ya, terima kasih kepada Profesor Nafarizal. Mungkin bisa dengan gaya, mau gaya apa? Terima kasihnya.
Ada gaya?
Kayaknya pada malu-malu nih. Padahal kalau biasanya, usually they give signs like this, and also others. But with the Professor Nafarizal, they
Shy ya?
Iya, shy lah. Ya, terima kasih. Mungkin begini saja. Terima kasih ya, gitu ya.
Ya, oke.
Nah,
Baik.
ya
Saya juga
silakan
ya.
diberikan
Ya.
ditampakkan mungkin separuh badannya ya, atau tangannya dikasih. Oke, saya take ya fotonya.
Oke, terima kasih juga ya, from my side.
1, 2, 3. Siapa yang mengambil saya ya? Oke.
Saya saja, Bu.
Oke.
Saya yang hitung.
Oke. 1, 2.
1, 2, 3.
Okay, thank you, Professor Nafarizal.
Okay,
I
you're
hope
welcome.
this last, even this is become the last class, but hopefully in the future we can still collaborate, and also the student can also contact with you.
Yes.
For the other opportunity.
Yeah.
Thank you very much.
Thank you very much. See you guys. Have a safe day over there.
Oke, thank you very much. Terima kasih semuanya juga. Saya akhiri kelasnya. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you, Prof. Terima kasih, Bu.
Iya, makanya sama-sama.
Sama ya.